So in this problem, we are supposed to find the stress in bar 1, normal stress, okay? Normal stress in bar 1, normal stress in bar 2, and the deflection of D. Now, when you look at this structure, we see that there is a 36 kilonewton load acting on D, causing the structure to tilt about an axis, okay, about point C, as such. Okay. Now this is exaggerated, and therefore, if I draw the displacement, it is just a straight line. Okay, so this is the displacement of bar 1. This is the displacement of bar 2. Okay, and then this is the displacement of point D. Okay, now we find that the displacement in bar 1 and bar 2, or displacement of A and B, are dependent on the axial deformations of bar 1 and bar 2. And so we find ourselves in a bit of trouble because this is a statically indeterminate structure, no? So when dealing with these kinds of structures, first we do the equilibrium equations, right? Okay, so we make our equilibrium equation. And we find that the summation of moment at C should be equal to 0 because this is a static structure. And therefore, there is a force in bar 1 going back, okay, going towards the support, pulling it back, and there is a force in bar 2 pulling it back also, but there is a force in acting on D that is causing the structure to tilt. So we will find that P1 times lever arm, that is 600 plus 350, so that is 950, plus P2 times 600 should be equal to 36 kilonewton. So I will make that into Newton. 36,000 Newton times the lever arm, 720. And this is our equilibrium equation. I will call this equation 1. Next, you have to find your geometry relationship by geometric deformations, no? And we see from this big triangle and this small triangle that delta 1 and delta 2 are directly related. So geometry formations relationships. So we find that by ratio and proportion of these two triangles, I will have delta 1 over 950 is equal to delta 2 over 600. Okay? After that, you have to find your deformation equations, or your deformation equation. So this bar will experience axial deformation and at the same time thermal deformation also, or deformation due to thermal effects, because the change in temperature of the whole system is negative 50, and therefore delta 1 is equal to P1 times A1 over PL over AE. PL P1 L1 over A1 E1, and delta 2 is equal to P2 L2 over A2 E2. So if I plug this into my geometry of deformations, I will have my compatibility. equation. Okay, and then I will have, oh, this is plus the thermal alpha plus delta T, alpha 1 plus delta T times L1, and then this is plus alpha 2 delta T plus times L2. If I plug this all in, I will have my compatibility equation, which is P1 L1 over A1 E1 plus alpha 1 delta T L1 over 950 should be equal to P2 L2 A2 B2 then plus alpha 2 delta T L2, and I will, it's all over 600. Now after that, we find that L1 and L2 are of the same length, 900, and therefore I can cancel this out. Okay, so I will have P1 over A1 E1 plus alpha 1 delta T over 950 is equal to P2 A2 E2 plus alpha 2 delta T over 600. So I can then substitute the values for A1, E1, alpha 1, delta T, and A2, E2, and alpha 2, because these are all given properties of your materials. So I will have P1 over A1, that is 400, times E1, that is 200, times 10 to the 3. I will make this into megapascal, so that if I multiply by mm squared, I will get Newton, because MPa is equal to Newton per mm squared. And take note that this is already in kilonewton, in Newton. So I change my kilonewton into Newton by multiplying 36 by 1000, just so that units will be the same. You should always take note of your units when you are solving. Okay, plus 11.7 times 10 to the negative 6 plus times negative 50. Okay, our change in T all over 950 is equal to P2 over 400 times 70 GPa, so that is 70 times 10 to the 3. Okay, plus 22.5 times 10 to the negative 6 times negative 50. Okay, all over 600. Okay, when I cross multiply, I will get 600 times P1 over 400 times 200 times 10 to the 3. Okay, plus 11.7 times 10 to the negative 6 times negative 50 plus equals 950 times P2 over 400 times 70 times 10 to the 3 plus 22.5 times 10 to the negative 6 times negative 50. Okay. So distributing 600 here and 950 here, and then I will transfer this term back here, and I will transfer this term back here. I will have 600 over 400 times 200 times 10 to the 3. Okay, P1 minus 950 over 400 times 70 times 10 to the 3. Okay. P2 should be equal to 22.5 times 10 to the negative 6 times negative 50 minus 11.7 times 10 to the negative 6 times negative 50. Okay, and simplifying, I will get 7.5 times 10 to the negative 6 P1 minus 3.3928 times 10 to the negative 5 P2 equals negative 0.71775. And we see, if I call this equation 2, we have two equations and two unknowns. So if this is equation 1, equation 2, go to your mode 5.1, your calculus, and you will have to input this into the calculus. So that is 950, 600, you will see it's like that. 3,600 times 36,000 times 720 over 7.5 times 10 to the negative 6, and then negative 3.4 times 10 to the negative 5, and then negative 0.71775. If so, you will get P1 equals 12.217 kilonewton and P2 equals 23.856 kilonewton. Okay, so therefore stress 1 is just equal to stress force over area. So I will have 12,217 over 400, and stress in 2 is 23,856 over 400. I made this into Newton because I can directly get MPa from this calculation, because 400 is mm squared, and therefore I will have 30.54 MPa in tension and 59.64 MPa in tension. Okay. So that is answered already. Okay. So next, how do you get your delta D? Now remember that delta 1 over 950 by ratio and proportion should be equal to delta D. Delta D over 720. Okay, so how do you get your delta 1? You simply input your values for delta for sigma 1 into this equation. I will just do this manually. So I will have delta 1 times L1 over E1 plus alpha 1 times delta T times L1 over 950 should be equal to delta D over 720, and you will find that your delta D is equal to negative 0.295 mm. This is negative because our assumption was that delta D is going down. Now, because it's negative, that means that our assumption is wrong, and therefore our delta